Okay, so we're going to start worksheet number, this is 14. Worksheet 15 now, about AC circuits, complex numbers, and EM waves. It's a super worksheet, right? It's a longer one. So at first it says we can represent a complex number z of the form complex number z. Usually z is reserved for a complex number as x plus iy. X is called the real part. Y, the thing after the I, this y, is called the complex part. Both x and y are real. Both the x and the real part of z are real. And also we can represent z. We can represent it as, we can always write it in this form as the absolute value of z and then e to some I theta. Some I theta. We can always write it that way. The absolute value of z is the magnitude of z. The magnitude of z is x squared plus y squared squared root. That's the magnitude of z. Okay. And oh yeah, the angle theta can be written as the tangent inverse of the y over the x, right? So that's what I mentioned at the very beginning. Okay, so let's go to problem 1. So part 1. Part 1, okay, just part 1. So suppose z is equal to just I, this number I, square root of -1. So that means they say write it in terms of the modulus of z, meaning what is the magnitude of z and what's the angle theta. That's what I want you to find. Z and theta. What would these two things be? So first, notice z is equal to this. 0 plus I times 1, right? Right? Z is equal to 0 plus I times 1. If I were to plot it on the xy plane, here's x, here's the iy, here's 1. So this is where I would stand. That's where I would stand. So what's the angle here? 90. So we conclude that the magnitude of z is this size. How long is this? 1, because 0 squared plus 1 squared is 1. So the magnitude of z is 1, and theta is what? 90 or pi over 2. We usually want to express it as a number between minus pi over 2 to pi over 2. So that is it. All right? All right.
Just a question that if you use the formula into the letter x.
This one?
Oh no, like the theta equals the tangent inverse of like.
Yes, yeah.
So like when you plug that in, wouldn't it be like undefined? Or
Yeah,
is
it would
like
be.
in the x y plane?
Yeah, it would be inverse tangent of positive infinity, which is pi over 2.
Oh.
Right, because you're divided by 0. Yeah, so, right, if you put, what is tangent of pi over 2?
The asymptote?
Yes, it would be approaching positive infinity, right?
Yeah.
Yeah. It's approaching positive infinity. Yeah. When it sits exactly at that, it is pi over 2. Okay. Any other questions? How about for part 2? If part 2, if z is equal to minus I, the easiest way probably is just plot it. Sometimes it's easier to plot when you have those just purely imaginary or purely real. Here's x, here's y, or iy. It's here, right? That's where this minus I is. So, what's the size of z? 1. And what's the angle? Minus pi over 2. Thank you. Negative pi over 2. How about this one? 43. Here's the next one. Let's say z is equal to r, right? R plus I times L omega. L is, so R is a real number, L is a real number, omega is a real number, and I is I. So you can think of R here, maybe it's 10. Omega times L, maybe it's 20 or 70 or something. So it's some number. So what can I say about Z?
It's the square root of r
Square root of, yeah?
plus L squared omega squared.
Yeah. Like so? Yeah. You take the real part is squared, take the imaginary part is squared. In this case, the real part of Z is what? Is R. What's the imaginary part? L omega, right? And how about theta? What can I say about theta? Will equal to tangent inverse of what?
L omega over r.
L omega, or omega L over R, yeah. Why am I using the symbols R and L and omega? Yes, to get us familiar and ready with the RLC circuits. For now, they're just symbols, right? Yeah. Let's do part 4 here. Z is R minus I over omega C. Omega C. Okay. So what's the absolute value of Z? R squared, plus. Yeah, so it's negative 1 over omega C squared, but the negative goes away when you square it, so you just get this one, right? Omega C squared. Squared. It's actually that one. Oh. Yeah, that one. And then the angle theta will be tangent inverse of what? Negative 1 over omega C divided by R. So it would be 1 over omega C times R, right? Or R omega C, yeah. Yeah, that's right. How do you like this so far? Not bad, right? So sometimes the real part of Z, we use this formula here. So if Z is equal to X plus IY, we say the real part of Z is what? RE means the real part of Z is what? X. And the imaginary part of Z is just the Y. Because the imaginary part is real. Okay. Then there is this thing called the complex conjugate of a real number, of an imaginary number. The complex conjugate. The complex conjugate. So if you have a real number z and you want its complex conjugate, sometimes the complex conjugate is written as z bar like this. Sometimes people write it as z star like this also. Z star. Both stand for the same thing. Here is what you do. It's pretty simple. Find where the I is and change its sign. If it's positive, make it negative. So you get x minus iy. That's it. It's x. What do you do? I'm sorry. If it's positive iy, you change the I into minus. So it looks like that. And I want you to notice the following. Notice that this z times z bar, z times its own conjugate is equal to this. Z is x plus iy, right? And z bar will be x minus iy. So what happens when you multiply them together? You get x squared. X times x is x squared. And then I times y times x. So plus I. I'm sorry. I need to do this one. Minus I xy, right? And then this times this is plus I xy. And then, how about this? What is iy times negative iy?
Negative I squared y squared.
Negative I squared y squared, okay. So negative, I heard I squared, y squared. But what's I squared?
Negative 1.
I squared is minus 1. So minus 1 becomes
Plus y squared.
plus 1. So it just becomes plus y squared. So these cancel, and you get x squared plus y squared. So that means this z times z bar is the same as the magnitude of z, right? Squared.
Right.
Okay. Okay. All right. So let's look at the problem 2. It says, suppose you have a complex number z, and it has a complex conjugate z bar, and they say, as shown in the figure. Here it is. So this is problem 4, right? Or 2. Sorry. Problem 2. Problem 2. Here is, this is 30 degrees, I think. Yeah. And this is z bar. And this is z. So if this is 30 degrees, this has to be 30. Why? When you do bar, what do? You just change the complex part from minus to positive, or from positive to minus, right? Which axis would have the complex part? The y or the x?
The y.
The y. So if y is positive 2 here, and you do the conjugate, you get minus, right? Or if it's minus and you do the conjugate, you get plus. So here is what they say. They're saying this. Suppose z times z bar is 4, right? Z times z bar is 4. And it says, calculate the real and imaginary parts. Find the real and imaginary parts of z. So what can I do? What do I know about z times z bar? How is it related to the magnitude of this? It's z squared. Yeah. So we know that z times z bar is this. It's the magnitude of z squared. Therefore what? The magnitude of z is 2. Yeah, just 2. And therefore, what? So if this is, the magnitude is 2 of z. This angle is 30. So what can I say about the x? Which is the real part of z. So the real part of z is what? What's the, if you have a vector of size 2, and the angle here is 30 degrees, how can you find the x component? Would it be positive or negative, first of all?
Negative.
Negative, and it's adjacent to 30, right? So it would be negative, the magnitude is 2, times the cosine of 30. I'm sorry?
So you can also just do cosine 210 degrees.
Yes, if you do cosine of 210, you take the minus sign away. Yeah, you can do that. And what is the cosine of 30? It's square root of 3 over 2, right? So this becomes minus radical 3, right? Okay, how about the imaginary part of z? Yeah, it would also be negative, right? It's here. So it would be minus, and then 2 times the sine of 30, right? And sine of 30 is a half. You get minus 1? Yeah. Let's see. Minus radical 3, yeah, minus. Okay. Any questions on what I have done so far? Okay. Let's go to problem 3. Now, yeah, let's do problem 3. Problem 3 is you have a number z. Suppose z is r plus I omega times L. And they're telling you that r and omega and L are all what? Real numbers, right? They're all real numbers. So the question is, find the real and imaginary parts of 1 over z. So let's first of all write down what is 1 over z. 1 over z is what? It would be 1 over r plus I times omega times L, right? So, but I can't really tell what the real and imaginary part at the moment is, right? At least not right away. So, I need to write it in the form of some real number plus I times some other real number. That's how I need to write it. So how do I do that?
Multiply by the conjugate.
Multiply by the conjugate, top and bottom, by the numerator. By the numerator and denominator by the same number. So here's what happens. So you do this, r minus I times omega L, and then r minus I times omega L. First of all, why is this equal to do?
It's just multiplying by 1.
Exactly, you're multiplying by 1, right? And 1 doesn't change anything. So good, so we can do that. So now, you get 1 over z will be. Yeah, so this times this, we did this earlier, right? Yeah, you get x squared plus y squared. So the x is the r, and the y is the omega L, right? So you get r squared plus omega squared L squared, right? And then in the numerator you have the r minus I times omega times L, right? So you can also separate this as follows. You have it as r over r squared plus omega squared L squared, and then plus I, this I, actually minus I times omega L over r squared plus omega squared L squared, like so. Is this okay so far? Okay, so I have my complex number now written in the form I like. The form I like is a real number plus I times another real number. So, is this a real number? Yes. So this is the real part. So the real part of this 1 over z will be r over r squared plus omega squared L squared. And the imaginary part of 1 over z will be what? Which one? Just take the I out and then put everything that's left. So you get the minus omega L over r squared plus omega squared L squared. That's the imaginary. Actually, let me ask this question. If you learn about complex numbers, in what course have you done that? Okay, in some math course, and I don't think you touched on them on Calc 1 or 2 or 3.
It's kind of early on.
It's
I
an,
don't remember.
so it has been a while.
Yeah.
Okay, then, okay, got it. Okay, so it has been a good while, right?
Yeah.
Okay. Yeah. Linear algebra, you don't learn about them, right?
No.
I don't remember. I mean, what's the difference? You see how a complex number behaves in many ways like a vector, right? It has an x and a y component, isn't it? Yeah. But it's not really a vector because do you have a dot product or a cross product? You don't really have them, right? Unless you want to define them. Yeah. Well, I'm glad you've seen them, you know, way back when, so that's good. The only thing you probably haven't seen in algebra 2 is Euler's formula, right?
Yeah, but that was Calc 3.
In Calc 3, I've seen this one? In one of the problems, okay. Yeah, I remember I saw it myself when I first learned about it in Calc 2 when we did Taylor expansions. Probably one of the homework problems also. It was it's always right, the important stuff is left as an exercise to the reader. So for the reader to do. So I think it was one of those exercises that were there. Okay. Let's see. So we did this, right? It says find the real, find the imaginary. We did parts 1 and 2, didn't we?
Yeah.
And then part 3, it should say find the angle, not find the imaginary part, because that would be asking the same. Huh?
Don't ask that one question.
Yeah, yeah. So for part 3, I wanted to say find the angle for part 3. So who wants to tell me how to find the angle? Theta would be what?
Inverse
Of
negative omega.
this
Yeah.
over this, right?
Yeah.
Good. And when you divide them, you see the denominators are the same, so they go away. So you end up with what? Negative what?
Omega.
Over R. Thank you. That's all. Yeah, that's what you end up. Let's go to problem 4. So here is problem 4. Problem 4. We got the following. We were given this. Z1 is equal to 3 plus I times 2, right? Or 2I. 2I, or I times 2. And then Z2 is x2 plus I times y2, right? I times y2. We don't know what x2 and y2 are. But here's what we're told. We're told this, that z1 plus z2 is equal to z1 complex conjugate. Z1 times the complex conjugate, or Z1 complex conjugate. So let's write down the equation. What is Z1? 3 plus I2, right? So Z1 is 3 plus I2 plus Z2 is x2 plus I times y2 equals And Z1 bar is what? What's the complex conjugate of Z1? 3 minus 2i, or I2. 3 minus I2, like so. Yeah. So now, for two complex numbers to be equal, you need their complex parts to be equal and their real parts to be equal, then they are equal, right? Just like two vectors. If two vectors are equal, it means their x components are equal, and their y components are equal, and there are z components, they're also equal. So, you got 3 plus x2 equals to 3, right? So let's write it down. 3 plus x2, and then here plus, you got I times 2 and I times y, so I times y2 plus 2 is equal to 3 minus I times 2. So you match them. This matches with that. So 3 plus x2 equals to 3, therefore x2 is what? Yeah, x2 is 0. And then y2 plus 2 equals to minus 2, right? So what is y2? Minus 4, yeah. And that's all they want. So the real part of Z2 is what? 0. And the complex part, or the imaginary part? Is minus 4, yeah. Okay. Well, now you're given two other numbers, Z1 and Z2, and you're asked to multiply them together. I'll give you a moment to do that while I write them on the board. We want to multiply these. So let's do it. What is 4 times negative 2 is what? Minus 8. And then 4 times I3 is plus 12i, right? Or I times 12 if you want. And then minus 10i, or minus I10. And then I times I is minus 1, so minus what? 15, thank you. So you got minus 23, right? And then plus 2, or I2, something like that. So the real part of Z1 times Z2 is minus 23. And then the imaginary part of this product Z1, Z2 is just 2, right? Yeah. Okay. We're getting in there. The next one is you got a complex number Z1. It's 3 plus, or 3 minus I times the square root of 3 over 3. And it says we want to express it using Euler's formula. So, meaning this. So, problem 6. You got Z1. This is problem 6. Let's see. You got Z1 is equal to 3 minus I, and then 3 radical 3. So we want to write it in the form like this. Sum to the, like this, the absolute value of z times e to the I theta. So in other words, you need to find theta and you need to find the magnitude of z. So, yeah. So for the magnitude of z, what can we say?
3.
It's what?
3.
Only?
Huh?
Is it 3? I don't know. I need to double check. It's like a little bit more.
Isn't 3 plus?
So you need square this, and add them together, right? So let's do that. So that, just to be clear, it would be like this, right? 3 squared plus minus 3 square root of 3, the whole thing squared, right? And let's see, 3 squared is 9 plus 9, and then 3, 27? 27 square root? 36, so 6. So the magnitude would be 6. Yeah. Okay. Okay. So 6. And then theta, you would have the tangent inverse of minus 3 radical 3 over 3, right? So that's tangent inverse of minus square root of 3. Like negative 30 degrees?
Yeah.
So pi over 2 is 6.
Okay.
It's 60.
Or 60.
Maybe I would.
Okay. So minus 60, so minus pi over 3.
Yes.
Yeah. Okay. So so in other words, how can we write it in this formula? So the absolute value of z is 6, and then e to the I times what? Pi over 3, yeah, so, or like that. Yeah. Yeah, minus pi over 3, yeah, you're right. Or part B now. Part B. With part B, it says, I think we did something similar to this. So for part B, you're given a number z2 is equal to e to the, no, not e, 2 times, 2e to the I times pi over 3. So you want to find the complex and imaginary part, so we need to expand this, right? So it would be 2 times the cosine of what? Pi over 3 plus I times the sine of, or actually 2i, right? I times 2, and then sine of pi over 3. Cosine of 60 degrees is a half, right? So this is just 1 plus I times square root of 3. Okay, so good. So we know we're right earlier. The tangent is 60. Okay. So that means the real part of z2 is 1, and the imaginary part of z2 is square root of 3. So let's go to the next part, part C. I'll try to do part C here. So you have a complex number z1 is 1 plus I. So z1 is equal to 1 plus I. And z2 is this, 5 e to the minus I times pi over 4, right? And we want to multiply them and then find their real and imaginary part. So first of all, we either have to represent this as a sine and a cosine, or maybe make this one into an exponential. It may be easier to make it into an exponential and then multiply. It's easier to multiply exponentials because you just add the powers instead of foiling. So this one is an exponential. So please, let's see if we can do this without writing. Let's see if we can do it. So we want to write this as something times e to the I times something, right? So what goes here? Here goes the magnitude of this number, of z. What's the magnitude of 1 plus I?
Square root.
Square root of 2. Because you do 1 squared plus 1 squared square root, right? So square root of 2. So this would be radical 2, square root of 2. Now what angle does it make?
Pi over 4.
It is pi over 4, yeah, because this. Here's 1, right? That's this one. And then the I will be here. So this complex number is represented here. It's 1 this way and 1 this way. So it's 45 degrees or pi over 4. So here goes pi over 4. Let's multiply them. So when you multiply them, z1 times z2, you will get, well, 5 times square root of 2 is 5 times the square root of 2. And then e to what power? E to what power? Minus I pi over 4 plus I pi over 4. How much is that?
2 pi over 4.
Not quite.
Zero.
Minus.
Yeah. So 0. And what's e to the 0? E to the 0 is 1. So you just get 5 square root of 2. Yeah. So what's the real part of this? What is the real part? 5 square root of 2. What's the imaginary part? 0. There is no imaginary part. So the real part is 5 radical 2. The imaginary part is 0. Okay. All right. I mean, you could have tried to write this as 5 times the cosine of negative pi over 4, and then plus I times the sine of negative pi over 4, and then multiply them together, and you would arrive at the same result. So, yeah. I'm sorry? Yes. You guys need a break in there, or should we continue till 2? Till 2?
I'll take a break.
Okay, let's do that.